calculating the mass of an electrolysis product from the applied current. Okay, so in order to do this, we're going to need to know our relationship between current, charge, and time. So current is how we describe a moving charge, and current is in units of amperes, and that is just the ratio of charge in coulombs over time, which is in seconds, of course. So essentially coulombs per second. So if we have this relationship and we have our current and our time, we can work out in this case how much charge has been accumulated during this period of time. If we know charge, there is a relationship between charge in coulombs and the Faraday constant and the number of moles of electrons. So charge is equal to N, the number of moles of electrons which are transferred during a redox process, and F, the Faraday constant. So of course N would be the amount of moles, and remember the Faraday constant is 96,485 coulombs per mole. So you can see unit-wise, coulombs per mole times by number of moles is going to give you charge in coulombs. One thing you do have to be very aware of here is stoichiometry. Okay, so we're talking about electrolyzing sodium chloride. So there's a couple of redox processes going on here. So one of them is going to be to do with the sodium, and the other is to do with the chlorine being produced. So the redox half reaction that we are interested in this case is going to be the oxidation of the chloride ion to produce chlorine gas. So that would be an increase in oxidation state from -1 to 0. So in order to balance this, we are going to have to add electrons to balance, and we're going to have to also adjust the mass. So because chlorine is a homonuclear diatomic Cl2 molecule, we know there's going to be 2 chloride ions required to form 1 mole of Cl2. That won't be a solid. What are we talking about? So honestly, it's probably going to be the gaseous state under standard conditions. So to balance the charge, we're going to have to add 2 electrons to this half reaction. So if we have the current and we have the time, we're going to be able to calculate the charge. If we have the charge and we know the Faraday constant, we can calculate N, which is the number of moles of electrons that are being transferred in this equation. And the reason I actually wanted to write out the half reaction is because we do need to take into account stoichiometry. For every 2 moles of electrons that are produced, you are only producing 1 mole of chlorine. So write down that mole ratio. It may not always be 1-to-1. Like here, it's a 2-to-1 ratio between moles of electrons and moles of our product. So do be careful. All right, so I'm going to calculate my charge then. So my charge in coulombs is going to be my current in amperes times my time in seconds. So that is going to be 400 amperes times 89.0 seconds, and that is going to give me a total amount of charge of 3.56 times 10 to the power of 4 coulombs. I'm going to have to make my box a little bit bigger here. All right. Okay, so now I have my charge, and that should be a capital C. Oopsie, didn't push down the shift key hard enough. So now I can rearrange and solve my number of moles of electrons being transferred, which is going to be my charge in coulombs over yon Faraday constant. Thank you, Michael Faraday. So that is going to be that charge, what we just calculated in it, 3.56 times 10 to the power of 4 coulombs. And the Faraday constant is in units of coulombs per mole. So we can see that we are going to cancel the Rooney here. Coulombs will cancel, and 1 over moles is just going to be moles. So we will get units of just moles, and that is moles specifically of electrons. And that shakes out to be 0.36897 moles of electrons. So then the last thing I'm going to need to do is convert that to moles of chlorine. So this is why I want that mole ratio. So for every 2 moles of electrons that are transferred, if I could type a 2, that would be helpful, wouldn't it? I will produce 1 mole of chlorine. And of course, this is just going to give you my number of moles of chlorine. So then I'm going to have to use the molar mass of chlorine, just like we did back in yonder days of old in Gen Chem 1, to convert moles of chlorine to mass in grams of chlorine. In terms of moles, that's going to shake out to be 0.18, blah, 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 of Cl2. We are almost there, okay? Of course, I could have just used the molar mass right off the rip, but let's just do it separately. So then I'm going to take the molar mass of chlorine, which is 2 times 35.545 or thereabouts. It goes to 70.89 something. Okay, 0.1. I'll just write my molar mass as a conversion factor just to be thorough. 1 mole of Cl2 weighs exactly 70.892 to the amount of sig figs I've got there. Okay, so then we can take that 0.18448 moles of chlorine and convert that into a mass in grams using the molar mass. 1 mole of chlorine weighs 70.892 grams. So that shakes out to be, what does that shake out to be? 13 point blah blah, 13.078-ish grams. In terms of sig figs, we said 3 sig figs, so I'm going to round that to 13.1, and that is good enough for me. Hopefully that's good enough for you too. And of course, as long as it's good enough for ALEKS, we are all happy. All right, so hopefully that is helpful for you guys. Just be aware of stoichiometry, okay? Because moles of electrons, you need to relate that to moles of the product that you're interested in.